Welcome to the pre-recording of Lecture 9 of MCS 572. So this lecture is one of the very last lectures in supercomputing in a chapter or in a part devoted to applications. So the title assumes more an advanced GPU topic, and in a way it is like that, but on the other hand, there will be a moment for applications. In this lecture, the central part is also a little bit how GPUs can be used also in connection with multi-threading. So the modern generations of GPUs support kernels running concurrently. And then in the last part, we make the connection with MPI, which is running GPUs with heavyweight threads processes. Okay, but first we have to introduce page-locked host memory, which is needed in the second part if you want to overlap communication with computation. So in a way, this comes at the end of the course. We also addressed this topic of overlapping communication with computation when we did the distributed memory parallel processing. Okay, so some terminology. So we have seen that in general, if you want to accelerate computations, help the CPU, what is available on the CPU in the random access memory of the CPU has to be transferred to the global memory, so the memory on the device. You can avoid this memory transfers if you work with page-locked memory. So memory, the random access memory, is paginated, so it's divided up into pages. And what it actually means when you have page-locked memory is that what is in that page is actually fixed. So the operating system actually divides the random access memory up into segments, and then also the segments are paginated, or actually segments and pages are what the operating system does. The virtue of working with page-locked memory is that one can overlap computations, the execution of the kernel, with actually the transfer of the memory. So we use also pinned memory, and the mapping of the addresses, so the addresses in global memory on the device and the memory on the host on the CPU in the random access memory, these address pages are actually mapped to each other. So that means that there is only one pointer that you can use to transfer. Normally you can't really do this, and that's one of the confusions with early GPU programming, which you still need to know. So in some sense, here is the bottom line. So pinned memory are actually a low priority optimization. So it's not something that everybody needs to know. Also, it's an optimization technique. And with all optimizations, some optimizations might not be always proper and appropriate. But it is appropriate and it is necessary even if you want to overlap data transfers with computations, as we will address in the second part. There is the other advantage, the benefit of the increased bandwidth, and this is what you observe here when you do a bandwidth test. So you see that the bandwidth tests happened actually with pinned memory transfers. So this was between memory that was page locked. And you see that on Volta, you have actually half a terabyte of bandwidth. So half a terabyte of 541 gigabytes per second that gets transferred. But that is from the device to device. From the device to host, this is significantly lower. These pinned transfers are still, you can see, 12 and 13, quite substantially less than the transfers that happen between the device. Okay, so the virtue of the previous slide is already that one can make sense what this utility, the bandwidth test, the terminology that appears on this bandwidth test, if you execute this from the software development kit on an NVIDIA GPU. Okay, so I will work out now a very simple C++ program to illustrate the usage of pinned host memory. So we program in C++, so there is the host, you still have to allocate, and you have to use one of the functions that is provided with the CUDA, so the Compute Unified Device Architecture. Also, you have to compile it with the NVIDIA compiler. So in order to map it, you have to indicate this when you allocate the memory. It is allocating memory on the device, but it's actually host memory, so it exists still twice. But the mapping is done explicitly when you do an extra call to this CUDA host get device pointer. So in particular, I should have illustrated this also, I should have emphasized this also earlier. So typically you cannot use the same variable name to access data both on the device and the host. But here actually this is something that you can do when it is mapped. And that's also actually what the mapping means. So the first thing that you do is to check whether this property is actually supported. There is the device query. So we will start. So actually, I ran this on the Volta, and the error code of the CUDA host alloc was actually 0. So that failure code was 0, no failure at all. And then you see here that also the mapping of the data went well, so there was no error. The failure code of the getting of the device pointer was also 0. Okay, so the first thing that actually we do is to check whether our device supports the pinned memory, and actually it does, because we've seen it on the device, on the memory band test. But how to actually check this as a programmer? So suppose that you write programs on one GPU and then they should also run on other GPUs. So this is how you could make your programs more or less portable. At the very least, you should provide for the possibility of errors and give a warning if the device property would not support the pinned memory. So in here is also where the device query, the code in the device query in the software development kit is very useful. So it provides you with examples on how you can explicitly test on this. Here is a very simple C++, or if you like, it's even C code, how you can check on the return value of the can map host memory. So this is simply a wrapper on this test, and it provides some extra output. Okay, so here is our simple kernel. So in a way, this makes this lecture self-contained. So we are running a data parallel algorithm. So we have a vector of 32-bit floating point numbers that we are going to square in essentially one single instruction. So we're going to launch a block of threads, and the ith thread will square the ith element. And actually it will override the ith element. So there are two instructions in this function. The function identifies, so it should point out the underscore underscore global underscore underscore, which indicates that this is a kernel. That kernel means it's launched from the host and executed by the device. So there are two instructions. So the thread identification number equals I, and that is used also to identify the data element. So in good data parallel programs, what every thread does is actually determined by its thread identification number. So we have a thread has a unique number within its block, but then we compute its global identification number. So this is a one-dimensional configuration of threads that gets launched. Typically, the block dim is a multiple of 32. So this can be executed on a very large number of threads. But we will just run it on one block of threads. We just want to figure out whether the pinned memory works. Okay, so here you see the main program. What the main program does, it executes the function with prototype just before the main. I will define that function in the next slides. So the main program checks whether the device supports the mapping of pages. And if it does, if the check was successful, then we will run our test function with 32 floating point numbers. So it will actually do this in the first 32 integer numbers. It will square them. Okay, so here is then the technical code. So the illustration of the CUDA host alloc. So we will allocate 32 bit floats. So every 32-bit float is 4 bytes. So we have 128 bytes. So that's the size of the total array expressed in bytes. And we must provide the CUDA host alloc mapped if we want to do the mapping at some point. So there is this variable x host. So the data exists on the host, and you see that we prepare the input by taking the first 32 positive natural numbers. So they are defined in that loop, I going from 0 to n-1, n-1 included, but then we add 1 to it in the loop. And we print out the content of the array. So in some sense this is plain C code. Alright, so now comes the second part of this kernel. Or actually the second part of the test function. You see the kernel is called in the square. That's simply our simple kernel. I said that the simple kernel is simple, but it's actually satisfied here. So in some sense, the kernel, in the definition of the kernel itself, the kernel, that definition is actually not really aware that it is page-locked memory. So here is now where we do the zero copy in the CUDA host get device pointer, and it's actually a very good name. It does what it says. It actually does the mapping of the host data, and it maps it to the device. And so you can see we go from the X host to the X device. And through this mapping, and here actually, so we call the kernel, so we actually have one block and one block of n threads. So in some sense, this is not really a code that you can use to check whether the performance is working. But now you see also the virtue when you synchronize the device, then you do not need to do a memory copy. You do not need to do a memory copy from the device on the host. Because of this, so we called the kernel of the on the X device, but when we print things out, we actually can print the code on the host. So we can write X host, and we will actually see the overwritten numbers. Instead of 2, we will see 4. So we see the values of the squares of the input. Okay, so the use of pinned host is, in some sense, does not require a modification of the kernel, but it replaces the CUDA mem copies that we did. Okay, and why would you want to do this? Well, this makes the transition to the second part, and also it kind of relates a little bit to MPI with message passing, where we had instructions send and receive that were blocking. So in some sense, the CUDA mem copy is a blocking data transfer. So you kind of suspend the control of the host thread, of the main thread of the host, which executes this. And that thread is suspended until the entire transfer is complete. So it is possible to overlap the data transfer with the computation using asynchronous memory copies. But for that, you actually need pinned memory. So in a way, the notions that we are using, so this is an entire GPU lecture, but some of the notions we have discussed earlier in the course. So data transfers between host and device are typically often the bottleneck for GPU computing. But you can alleviate these bottlenecks if you can chunk up your data and then start processing some of your data before on the chunks already. So in some sense, this is another example a little bit about pipelining, a topic that we have seen also earlier. Okay, streams and concurrency. In some sense, the different streams that execute concurrently, in some sense, the word concurrently is now a little bit ill used, so I'm using the terminology. So it's kind of an unfortunate word, I will say, because I typically, so I copy this from the CUDA programming guides, and they use concurrent executions. Concurrent executions are things that happen at the same time, but so the example is the polite dinner conversation. That's the clearest example I can give. So during a polite dinner conversation, there are two things that are happening concurrently, that is eating and talking, but they don't happen at the same time. So it's a polite dinner conversation. You do not talk with food in your mouth. So that may that is opposite to multi-threading, where you would talk with food in your mouth. All right. So I prepared this slides earlier runs of the course when I was using Kepler, and there I got that 4 was the number of maximum streams. I have been unable, or perhaps a little bit too lazy, to check what it is on the current GPUs, but I would gather that it's still 4. So here actually see the concurrent kernel execution. So in some sense, uh, what you actually are doing is indeed the time, so the total, so in the serial kernel execution, you see that there is a lot of idle time here if you execute these kernels one after the other. But if you execute this concurrently, you can kind of fill up the gaps. So in some sense, the word concurrently often assumes that there is no speed up, but here actually there is speed up with this concurrent kernel execution. In a way, you fill up the time. You make better use, so you occupy your GPU better. That's another way of seeing this. All right. So here is the overlapping between the data transfers and the execution times. While the transfers are happening, so what needs to be done is that, and in some sense, this is also a prerequisite on the type of computing that you do. So we are going to, you see the green and the red. So our type of computation needs to be such that we can process it in chunks. So that means that so in some type of computations, it only makes sense to start processing, to start execution when the entire data has arrived. If that is the case, then there is no benefit of doing this. But if you can chunk it up, if you are summing data or if you're processing data, then that can be processed in chunks, then there will be a benefit. There will be a benefit in particular when you can see that during the computation time. So here it's actually quite nice in the sense that your problem actually doesn't need. I take this back. Notice that the red bar is just as long as the green bar. So the number of computations that you are doing needs to be actually still sufficient. That's another strong prerequisite here. So in the course we made the distinction between compute bound and memory bound. If you're only going to add up two vectors, then that's actually not a really good candidate, I should also say, because the transfers between memory, so the bandwidth transfer, even for pinned, was still expressed at on Volta 12 and 13 gigabyte per second, whereas Volta and peak performance operates at teraflop performance. So it's important that your red needs to be, in some sense, the total time is the same, but if you look at the arithmetic intensity, then the arithmetic intensity of the red needs to be significantly larger than of the green. So that's kind of the caveat here. I will not time my computations here, and I will take again the squaring of the numbers, our running example. So here you see, again, one needs to check whether not only does your GPU support the mapping of the pinned memory, but also whether it supports the concurrent kernels. And here you see the output. Indeed, my Volta 100 supports concurrent kernels. Okay, 80 multiprocessors, compute capability 7. And I'm just squaring 16 numbers with 4 different kernels. And you see that the output is correct. So this is mainly showing the features. Here again, we have our simple kernel. So if so this lecture is self-contained. So this is a kernel which can be shown in a first introduction on GPU computing. Now, the main difference is that there are 2 arguments. So there is an input and there is an output. There is an X and there is a Y. And that modification was kind of necessary or perhaps it was not, but I think it was more convenient to illustrate the streaming. All right. So checking whether the concurrency is supported. This was again copy that was adjusted from the device query. So if you look at the utilities, the source code is there in the software development kit of NVIDIA, then you can see that the flag of the CUDA device property, the concurrent kernels, is something that you can check on. And what this wrapper function does, it actually is going to give the value of the flag. Actually, it's going to say that this GPU is supporting concurrency or not. It's also printing out the compute capability, so there is a major and a minor, and it's going to say actually also the number of multiprocessors that are available. So in some sense this is nice to look a little bit. So we spent a lot of time in this course also on multi-threading. So this is how you could also use the concepts that we have seen with multi-threading. Okay, so then here we have the main program again. So the main program is very short, a couple of lines, and it will call the test launch kernels. The first line is the test program that will be done, that we will only launch if the device actually supports the concurrent kernels. All right, this is another illustration of pinned memory. So in the middle of the slide we have the allocation, but now without the extra flag. So it's another use of pinned memory. We're going to transfer the data in an asynchronous manner in chunks. So that's why we are not going to have the mapping of the device pointer. We're not going to have the getting the device pointer. So we have 16 numbers, 4 streams that we're going to use, and the chunks are size 4. And again, I should worry that saying that this is a proof of concept to illustrate this feature, but squaring numbers is not computationally intensive enough. The application where it would work would, for example, be numerical integration, where on every piece of data you will do a complicated function. You will run a complicated function. We have the X host, and then we have the X device and the Y device. So the X host contains all the data. The X device will have the input that will be transferred in chunks, and the Y device contains the output. So then here you see the asynchronous memory transfers. So we have 2 loops, and this is also asynchronous in the sense that I think probably something seems a little bit off. So we will create the streams. And then we have the two loops. Now I think what is off, I think what should have happened, instead of having two separate loops, I should have fused the two loops. Although it may actually still run, in the sense that if it is asynchronous, it will not be blocking either. So it will simply launch those streams. Here you see now we square and we launch one block. And the nice thing is that we can actually indicate the start and also the end. So there are extra parameters in the launching of the kernel. One block, the size of each chunk, and then we have the beginning and the end element. So we do some pointer arithmetic in the calling of this kernel. All right. Then we have the device to host. So also here we have the streams that are doing this. So in a way, that's another way to speed up this data transfer. Calling into mind the last lecture on the disk parallelism, you have slower access. Well, actually you do. So I think that it will give you, in theory, speed up, provided that you do this on a compute intensive computation, on a compute bound operation. But it will give you speed up because you have the parallelism in the data transfers. It will probably here also be too little to notice. 16 and 4 chunk sizes are actually too little. But you see, you have the asynchronous copy again, but now from the output. So in some sense we have an X device, a Y device, but we have only one X host, so there is not a Y host. So on the host, the output, what is computed on the device, gets actually written back to the input data. We have to synchronize here, and in some sense this is a little bit similar to what we did earlier with the MPI barriers when we were doing the print. So in some sense we have to wait. So these are non-blocking data transfers. We have to wait for all these non-blocking transfers to be finished before our print will actually print out the correct numbers. And if you're doing this regularly for many times, so it's a good practice when you have allocated, when you have created the streams, that you destroy them and that also you deallocate all the allocated memories. Okay, good. Here is another feature. So I've been reading the CUDA programming guides. So I have, for what I have been explaining thus far, little actual practical experience. So these are the newer features of the GPUs. The Volta GPU has a multi-process service. So, and here is where the application, the moment of applications comes in. Notice the deep learning inference at the bottom of the slide. So the multi-process service is a little bit misleading in the sense that you could think of multiprocessing as an operating system, but this is for one single user. So if a user has multiple applications, then the GPU can be used and can be fully occupied, can be kept busy by having multiple applications. And here is where you have coming in the more higher level aspects of GPU computing, where you can launch many different types of kernels now within one single application. So the number of clients that you can have has increased on Volta to 48. So for if you have a batched system, and if you do this in a deep learning application, so this can have a very high throughput. So in some sense, this is how the parallelism can actually help in typically memory-bound computation. So the images are used as a reference. So if you have a deep learning experiment that processes a lot of images, then you have to load these images all the time in and out, and you do several operations on them. All right, so here is a picture that I stole from the Volta architecture. So it was already available on Pascal, but with Volta it has a better time sharing and also a better quality of service. So you can see that there is this separation of the resources of, you could see also, you can interpret this as similar streams. So it actually does some time sharing concept that we know from operating systems, but now executed on a GPU, which makes a GPU much more versatile for various applications. Okay, I have about 5 or 10 minutes left to go to the last topic. How you can work with multiple GPUs. So I talked about Pascal and Volta. One of my earlier graphics cards, one of my earlier workstations that had multiple GPUs, coming from a time when the National Science Foundation was very generous to me. So you can see that there are actually 3 graphics cards in there. One of them is NVIDIA regular commercial graphics card, so the GeForce GT6020 that was serving the display attached to this workstation. So you see that there are 3 CUDA capable devices. So for discount devices to work, also the regular, if you have a separate card that also serves the display of your computer, then that will show up as well. All right, so the device query is again very useful. So in some sense, coming a little bit full circle in this course, we can only scratch the surface, but we start now to see a little bit better as a programmer how we can take full advances, better advantage of the device query properties. And at first we ran these device queries at the very beginning to see what our GPU was capable of. Now actually we see we can actually check for all the devices the properties. So that is done in the C program here. And this is also done for all the, this is done after the CUDA get device count. So this will this will give the count of the CUDA enabled GPUs that are inside your computer. And for every one of those devices, you list the main properties. Okay, so I'm towards the end now. How do you actually work with this? So every computer has graphics cards, often multiple. So nodes in a supercomputer will often have multiple GPUs, and they will support multi-threading, and as nodes in a supercomputer, they are connected to other nodes. So one can work concurrently with the several GPUs with lightweight threads. So we've seen OpenMP as kind of the very good universal standard now. P-threads, if you are capable with systems program, is another alternative. So these are lightweight threads that do not require that much overhead, but where you have to be careful about sharing memories and race conditions. If your program is not thread safe, then you can resort to processes, also called heavyweight threads, where every process can actually have its own heap of allocated memory. So these are the tools that we have. So you can select the GPU from the beginning, which GPU you would like to use. And here I will defer to the software development kit of NVIDIA that has some simple multi-GPU tests. Okay, so this is my last slide. The main reference is indeed the NVIDIA CUDA Best Practices Guide that will get you deeper into multi-GPU programming. So I thank you for your interest in this lecture. I hope this was useful.